Hello, everyone good? Yes? Excellent. So my name is Richard Warburton. Just in case you haven't guessed already, the rest of this talk's going to be in English. And it's on production profiling. So a lot of people use profilers today, and they use them in a desktop environment, and they use them in your development environment. And we're going to be talking about a different approach here, which is using profiles in production. So first of all, I'm just going to talk a little bit about a very high level as to why performance might matter to your organization to begin with, why application performance is interesting. Not just from a technical point of view, because obviously it's fun kind of problems to look at from a technical point of view, but also from a business point of view. Then I'm going to have a talk about why development and production are different. Why would you want to do profiling in production rather than on your laptop or your desktop? And then we'll have a look at some other production performance monitoring approaches and talk a bit about how we can do production profiling really well, really effectively. Okay, so the first reason why you might want to have a performance consideration, why you might want to care about performance, is your customer experience. Being responsive to customer requests keeps them exceedingly happy, as does avoiding downtime problems. So who here uses like WhatsApp to talk to their friends and family? No WhatsApp users, some WhatsApp? What about Facebook? A few people? Who uses Friendster? No one. Why does no one use Friendster? Because it doesn't exist as a company anymore. Why does it not exist as a company? Because as they were trying to scale out their social networking business, they had consistent downtime problems due to the performance of their software, causing them outages. Really bad customer experience, ended up going nowhere as a business. Responsive applications make more money. So both Amazon and Google have done some really interesting studies, some A/B tests on production systems, where they looked at the impact on their business, what slower sites would be. So Amazon, for example, did an A/B test where they added 100 milliseconds of latency to the load times of their Amazon store where you buy stuff. And they found that sales dropped 1%. Now 1% doesn't sound that much, but for a business Amazon size, that's a huge amount of money. And that's just 100 milliseconds. That's a very short period of time. That's like, I'd like to click my fingers, but it's faster than me clicking my fingers, right? That's how fast it is. Google added 500 milliseconds to their search page generation time in an A/B test, and they found that traffic dropped by 20%. That's right, we are so impatient that we'll just browse away to another website if we have to wait for half a second. That's really important. And the other aspect of that is reducing costs, reducing specifically infrastructure costs around your system. Now, who these days is deploying to some kind of cloud-based environment? Quite a lot of people. Everyone loves the cloud, right? Or maybe not loves it, but everyone's using the cloud, right? Even if you don't love it. And what does cloud mean? It means billing by unit of compute time. That's fantastic because you can scale your bills up and down elastically. But it's also not so fantastic because you can scale your bills up elastically, right? So reducing costs for infrastructure becomes more important in a modern cloud environment than it used to be in the past. Cool. So I've gone through my boring set of business reasons to convince you to care, and probably a lot of people really care because it's technically interesting, but let's talk about the more important thrust of this talk. Why development and production environments aren't the same in terms of the way your application performs, in terms of the way it behaves. Because a lot of people, we run things like unit tests, automated tests on our development environment that check that our code works correctly, right? So how does it differ in terms of performance from business functionality? Well, as I say, testing and development's familiar and it's easy, and tooling for performance analysis is often a desktop-based tooling, like desktop profilers, monitoring systems. Development in profilers are a desktop-based tool. And it's not really a representative environment compared to your production system to run things on your desktop or your laptop, your regular development environment. There's a number of different reasons for that. Firstly, there's unrepresentative hardware, right? So who here has the same hardware on the workstation that they do their coding on as they do in production? One, but two people. Well done. Well done, that's really good. Sometimes it's almost impossible to even do that kind of representative hardware if you're running a cloud-based environment these days, because you don't actually know what hardware is being used under the hood by the cloud manufacturers. But in practice, this hardware differs in a lot of different ways. So firstly, you might look at the CPU speed of the machine itself, or for example, a number of cores on the machine that you encounter. Now, why would that be a problem? Well, you might find, say, on a laptop where you've got a couple of cores, that you can get away with having, for example, bigger, more coarse-grained locks in your application. And you wouldn't notice a big performance problem from there. It wouldn't matter so much if you have so many threads contending over them. Whereas if you're running it in production on, say, a 64-core server, and you've got all those 64 cores contending on a single lock somewhere in your application, you can rapidly run into very, very different performance characteristics from your development environment. Another way that you can see performance differences is, for example, the ratio in terms of speed between an SSD, like this laptop, for example, don't want to boast here, but has an NVMe SSD drive, right? Which is very, very common. You go to a lot of servers in data centers, they don't have SSDs. A lot of the people don't want to upgrade like their whole data center in one go, so they'll be still running on spinning bare metal. And as a result, you might get a very, very different ratio of CPU to disk I/O bottlenecks when you run your system between development and production. Another aspect of it is unrepresentative software. As this diagram shows, so I guess a lot of people are running Linux in production. As this diagram shows, there's a lot of different versions of Linux out there, right? So my next question to everyone is, who's running the same versions of their software, I mean their whole stack, OS, JVM, whatever, on their development environment as their production system? A few more people, that's good, that's good. But if, for example, you're running Windows or Mac OS on your development environment, and then running Linux on a server system, you can find wildly different performance variations between those two things. About 3 weeks ago, there was a Windows security update that got released for Windows 10, and it entailed a 40% slowdown in UDP traffic throughput. 40% for a single version. There was also the Spectre and Meltdown patches that came out earlier this year, and those again showed how you have different versions of the same software, even if you're running Linux. Just a more up-to-date version, or running Windows in both environments, a more up-to-date version can have dramatically different characteristics in terms of performance. So an unrepresentative software between your development environment and your production system can lead to you analysing things the wrong way, coming to the wrong conclusions about the way your software performs. Then there's unrepresentative workloads. If you want to take a desktop development environment, or even a QA system, a UAT system, and figure out how the performance problems that you might have in a production system relate to that, you need to be able to have some workload to run against the system. A performance test, some harness that's exercising your system and running some traffic against it. Performance testing is a pretty specialized skill. There's some people who are exceedingly good at it, professionals. Anyone a professional performance tester? A few people? Awesome. That's it's a great job. Now the problem is that it's really, really, really hard to do performance testing. It's really hard to get a representative workload of a production system. Okay? You often find that very, very subtle differences between the way your test harness performs and the way your production system performs can result in very, very rapid, very, very different results from your benchmarking. For example, a lot of people will run performance tests and they'll just have 1 or 2 users on their system that they run their performance tests against. And the problem with this is they might find some of that user data fits nicely in an in-memory cache somewhere. And in production, where they have a much wider range of different users, that those things don't fit in cache, and they get a very different performance characteristic. Another way it may be different is by having different numbers of users hitting their system at the same time. You may be able to replicate the rate at which people use your system, but not run them from different machines and not exercise different behaviors within, say, the TCP stack of your operating system. You can also get things like different patterns of behavior, how your users operate your system in production, what pages they go to on a website, for example, can be very, very different to the way those things work in a load test or a performance test. And people are notoriously bad at getting performance testing right. It's a really hard, really specialized skill. So you may not do it. Finally, the JVM may have different behavior in terms of production systems. So for example, Hotspots, the kind of Oracle OpenJDK JVM, does adaptive optimization. So what does that mean? It means that as your code's running, it profiles what that code is doing. It takes a track of certain behaviors in the application. It looks at how frequently methods are called. It looks at whether certain potential implementations of interface methods are ever used. And it will optimize adaptively based upon those different implementations. So for example, if ever you have a different logging configuration in production or in a performance test situation, the JIT compiler may be able to remove a load of code from that production system that it won't do in your UAT or performance testing environment. A really interesting example that I saw that really shows the hotspot, or a couple of examples actually, that shows the way Hotspot does adaptive optimization are one person I know who took their software that was running on Java 7 and they ran it on Java 8. And it was 10 times slower. 10 times slower, the same software, same hardware, same configuration. What changed? Well, Java 7 defaulted to server mode for its JIT compiler. Java 8 defaulted to tiered compilation. He flicked the switch back from tiered compilation to server mode, regained his 10x performance. Just that one subtle configuration example had a huge impact. It's a very extreme example, but an interesting one. Another example I saw was a system which had a clustered environment. And it had different machines, and one of the machines in the cluster was the leader of the cluster, strong leader. And if that leader fell over, the cluster would automatically elect a new leader from one of the other machines. But those other machines didn't run all the same business logic that the leader did. So as the leader fell over to a follower, the new follower got re-elected and became the new leader, the JIT compiler came along and had to do a load of on-stack replacements and swapping out compiled methods for other implementations of methods, because behind the hood, by switching from a follower to a leader, it swapped an implementation of some interface that had never been seen before by that runtime. So sometimes you can find these kind of things have very, very different behavior, and if you're not careful, sometimes those things can really bite you. Cool. So hopefully at this point, I've scared you enough about doing performance testing outside of a production environment. And so you might want to say, well, how do we understand the performance behavior, the performance characteristics of our system in production if we don't want to look at it in development? And that's where people normally turn to monitoring systems, right? And monitoring systems can gather a variety of different pieces of information. Most basic piece of information that you might see are ambient or passive or system metrics, whatever you want to call them. Metrics. Just numbers that you'll see that you'll record periodically from your application. So, for example, CPU time usage or user system CPU time breakdowns, page load times, things like that. So who keeps some kind of metrics from production systems that they run? Quite a few people, some people. Some people got a hands half. What's a hand half up mean? Does that mean you calculate metrics from some systems and not others? Who knows? Cool. Yeah. metrics are very cheap. When I say cheap, I don't mean cheap in money terms, I mean computationally cheap. They don't have much overhead in order to gather, and they can often be really effective. They can narrow down from wider performance problems into narrower things that you see. But if you use some metrics to narrow down a problem, you might want to go, well, where in my Java application is that taking up time? What bit of the stack is this actually using? And that's where people often turn to instrumentation-based approaches, traditional application performance monitoring systems. So the way instrumentation-based monitoring tools work is somewhere in your stack, they'll go, aha, I see you're using Spring Boot over there. So I'm going to find some key points in your Spring Boot app, and I'm going to add a little bit of code in and measure where the start time to, say, the controller in your app started and when it finished. And then they can measure those specific things that they've instrumented, similar with SQLs, queries, and all sorts of things. Instrumentation can be very useful, it can be very detailed, very actionable, right? As when I say actionable, I mean you can look at the information and say, aha, I know exactly where in my application to fix the problem that I'm seeing. But the big problem that instrumentation has is the more you add instrumentation to your application, because it's going to add little bits of measurement code inside your application, the bigger the overhead on the system is. The more fine-grained you go, the slower it gets. And you can rapidly go from becoming the solution to the problem to the cause of a performance problem. And there's production profiling. So I don't think very many organizations do production profiling for a variety of reasons we'll talk about later. But let's discuss it for a bit. So production profiling is a way of measuring what your application is behaving. Not by instrumenting the system as such, but by sampling or measuring what's going on in a more general way. So for example, what methods in your application are taking up the most CPU or taking up the most wall clock time? What lines of code in your application allocate objects? Where's the object allocation coming from? Where's the root cause of your memory leak, for example, if you see a memory leak coming from? Sometimes you can profile more esoteric things like on-CPU cache misses or instruction retirement rates, all sorts of things. Profiling can be automatic, no complex setup. If done well, it can be really computationally cheap, but as we'll see later, usually isn't. It's usually too much overhead for people to run in production. Now, I think one of the things to note about a lot of production performance monitoring systems is there's a little bit of a trade-off between the information that you get. Are you familiar with Goldilocks and the Three Bears? Or Goldilocks and the Three Pigs in some countries? Yeah? No? Okay. So, yes. So Goldilocks goes, and there are 3 bowls of porridge, one of them's too hot, one of them's too cold, the other one's just right. And you kind of find this often when it comes to the production and monitoring information side of things. If you have too little information, if your porridge is too cold, you can't really understand your production problem. You don't have observability. And the downside is that if you do get a production performance problem, then it takes your development team a long period of time in order to identify what the root cause of that problem was, or what the multiple causes of that problem were, and fix them. You get what people call murder mystery style debugging. I don't know if you've ever encountered that term. But you know at the end of certain types of murder mystery novels, the key detective, they go around and they say, was it you who did it? No. Was it you who did it? No. Was it you who did it? No. Was it you who did it? Sorry mate, I'm picking on you. Yes, you're the murderer. It's okay, you're not really the murderer. Maybe. Anyway. And that's the kind of performance investigation you often get. You look at different things and start going through on an ad hoc or hopefully systematic basis and see what is the thing that's going wrong. It takes a long time. You want to get more rapidly to the problem. Save development time, get things working quickly. But if you have too much information, if your porridge is too hot, then you get the other side of the situation, which is the needle in the haystack problem. Instead of just guessing a few different options, you start looking at lots and lots of different metrics, and you can't figure out exactly what the root cause or the root problem is. Perhaps you become the problem. If you have too much overhead on gathering this information, you can often become a cause of performance problems yourself. So you've got a bit of a trade-off there. You want to understand what's going on without overwhelming yourself and without overwhelming the system in question as well. Another problem people often encounter are unactionable metrics. So sometimes I've seen organizations that have these beautiful big dashboards, like massive 40-inch LCD, 4K, lovely budget. And on this dashboard, you get a lot of graphs as to what the system's doing, right? Which can be good, yeah? Sometimes you can see what's going on and you can observe what's going on in the production system. But sometimes you find metrics that don't help you progress treatment. They don't let you identify the cause of your problem, okay? You can't really see what's going on there. And, yeah, it can be a problem. Another problem you encounter is this normalisation of deviance problem. So who's worked in an organisation where you've had some failing tests, and the solution to the failing tests was just to ignore all the tests? It's okay, be brave. I'm amazed more people aren't putting their hands at this point. Fantastic, great. But sometimes this kind of thing happens in organisations. And I think you get a similar problem with alerting from monitoring systems. Some of the alerts get triggered regularly, so you just ignore them. Sometimes you pop into an organisation, you see those beautiful dashboards, and they've got like green and red and amber blocks. And if you've got green and red and amber alerting systems on a big dashboard, you want everything to be green, right? Like a forest. You don't want it to be like a mixture of green and red, like a Christmas tree. You go and see these Christmas trees, and you're like, so why is this thing here red? It's like, I don't really know why it's red. That one's always red. We just kind of ignore it. We just leave it going. Is that a good thing to be alerting on? Either it's broken and you want to fix it, or it doesn't matter that it's broken and you shouldn't be measuring it, you shouldn't be monitoring it. You don't want it on your dashboard, you don't want to have that kind of alert. So I think there's a normalisation of deviance problem here. We have false positives, things which are alerting that aren't a problem, that have a cost that we think. Because people, after a while, if they get too many alerts, they just ignore them anyway. Now, surely there's a better way, a better approach that we can think of when it comes to performance monitoring. We said that metrics are really useful. They can help us narrow down problems, but they don't necessarily get us to where we are in our code base. Instrumentation was really useful for solving that narrowed down problem, but it was hard to get low overhead instrumentation that was really fine-grained, that really told you where in your app the problem was going on. So let's look at how we can use profiling to solve that kind of problem. So, how would we use a product? Let's deal with some of the technical issues in a bit. How would we use a production profiling system? Well, you identify that you've got some performance problem that you want to figure out how to solve. You want to see what's going on with your production system at some point in time. So you need to narrow down a time period and some specific machines or applications where you have this problem. You can have a look at the different types of profile on offer. So profiles can expose information about a variety of different things, different types of CPU time. So when I say CPU time, I mean what's actually being run on the CPU. Different types of memory allocation rates, things like that. You want to kind of figure out where in your code base the dominant consumer of a given resource is. So what's the bit of code that's actually using up the CPU? What's the bit of code that's not using up the CPU because it's sat there blocked and waiting for some system? What's eating all the memory? Once you've found that bottleneck, you can narrow down the bottleneck, solve it, hopefully deploy a fix, and then iterate around that kind of problem. So I made a distinction between CPU time and wall clock time, which are two different ways you can think of for profiling data. So what do I mean by CPU time? CPU time is, the actual time that you spend with your code running on the CPU. Now, unbelievably, most Java profilers don't actually tell you what the CPU time is at all. We'll talk about that in a second. War clock time is the other aspect of it, which is how much time is your application spent stopped versus running. So the way I like to think of it is like a coffee shop. Okay? The CPU time is the time that's taking to actually make the coffee, grind the beans, foam the milk, pour the foamed milk into the coffee with a little bit of latte art at the end, which I can never get right. War clock time is like the whole thing. It's like standing in line at the queue, waiting for them to take your money, paying the person the money, standing in another queue, waiting for the coffee to be made, your coffee then being made, then you picking it up and walking off with it. It's like the whole time that you're using your application versus the time on CPU. And these are different things that a profiler can offer you, tell you what your code is using up those things. So what kind of visualizations do profilers offer? There's a traditional kind of hotspots or flat view on a profiler. So for example, a list of the methods or lines in your application and telling you how much time in your application is actually being allocated to that specific method. So this profile is telling us that 8% of the time in the application is being spent on getting the entries out of a zip file, for example. Another view that some profilers offer is a tree view. So tree views are a stack, a call stack of different methods inside your application, where further up the tree are methods that call methods lower down the tree. So at the top, you might say, here, for example, java-lang thread.run, because that's what's calling all the other code in your different threads. And then as you go down the tree, you'll see what's calling what, and have an allocation of how much time is being spent in total, like for that node and its children, versus just how much time that node itself is using up, how much time that method is using up. Then there's flame graphs. Flame graphs are a pretty fancy new visualization around profiling. Has anyone used flame graphs before or seen flame graphs? Cool, a few people. Awesome, awesome. So, flame graphs are a visualization that was, I think, originally invented by Brendan Gregg at Netflix. And the idea with a flame graph is it combines a nice kind of call stack aware tree view, hierarchical view, with also a visualization of how much time is being used up. So at the top of your flame graph, you can see, for example, what the top method is that's being called. So we're going top down. Some flame graphs start with this at the bottom and go up. And then as you go down that flame graph, methods lower down the flame graph are being called by their parents. And how wide they are reflects how much time they or their children spent. So you can see, for example, here, that when we accept that socket, that is using a load of time up because it's a lot wider than its child method there in yellow. So flame graphs are a really good visualization that let you see what's going on in the application system and see which methods are using up more time in your application. Help you narrow down to the cause of a performance problem. Okay, so I think some people are familiar, most people are familiar with having used profilers at some point in time in their lives. But the probably more interesting question is, how do they work under the hood? Because the key problem that different people have with profilers is they may take more or less time up in terms of slowing your application down, and often the overhead from profiling is too high to use in production. The most traditional type of profilers are instrumenting profilers. So if you use JVisualVM, you click on the profiler tab, it will be an instrumenting profiler. Instrumenting profilers, as I say, similar to the APM instrumentation, they'll add timing measurements at the beginning and end of every method in your application. And they'll slow them down by a fixed amount per method. So A, that has huge overhead. Instrumenting profilers can make your system twice as slow, sometimes 3 times slower than they were otherwise. And secondly, it totally modifies the performance behavior of your application. If you've got a really short method, like say a getter, that just reads a field out of an object and returns it, then the timing measurements at the beginning and end of that method will totally dominate the method time of just reading out the field, because it takes you more time to actually record the timing information. If you've got a really big method that's doing loads of things, then the overhead of that instrumentation code will be really small by comparison. So instrumenting profilers make short, quick methods look much longer than they actually are in comparison to really long methods. They totally bias your view of the profile. So, a lot of people use sampling profilers or statistical profilers. Don't worry, you don't have to be a statistician to see what the output is from statistical profilers. So, I love statistics. Some of my best friends are statisticians. Anyway. What do sampling profilers do? Your application is running along, and they periodically interrupt the application in order to read what the core stack is at that point in time. They walk the stack, keep track of it, and then aggregate that picture over time. So if they've seen a method in a core stack more often, they know it's spending more time there. And if it's the method that's actually being executed at the time, that's the self time of the method. That's its code actually being running, and things up the core stack are things that call that. So you just build up a statistical profile from aggregating those samples. Now, Java itself has a bunch of standardized APIs for doing profiling. Most profilers use, for example, the JVM-TI APIs, or you can get this information from pure Java code using MX beans. But the MX beans under the hood basically just call the JVM-TI code in order to get stack traces. So there's a JVM-TI method called getAllStackTraces. So what does getAllStackTraces do? Well, it gets you all the stack traces of the threads. Great! What's that really doing? Well, it's a blocking method, you see. So in order to record all the stack traces for your application, it needs to get the threads in question to stop. It needs to read their stack traces, and then it needs to return that value to you. So how does it stop the threads? It uses what a JVM mechanism called safe points. Quick hands up, who's heard of a safe point before? Oh, excellent, excellent. So if you've not heard of a safe point before, don't worry. There's no, in many ways you shouldn't have had to understand what a safe point is to write Java code. But a safe point is just a mechanism that JVM uses to bring threads to a halt. So periodically, inside the code that your JIT compiler emits, it will do a read to a specific page of memory somewhere. It'll just read the value out of that page of memory. And that's a safe point poll. When the JVM wants to interrupt those threads and bring them to a halt, it takes that page of memory and it protects it. And it puts an interrupt handler on that block of memory. And then that interrupt handler will be called the next time a bit of code reads that safe point poll. It reads a byte from that page. So what does this mean? It means that getAllStackTraces, far from telling you what the stack trace is at the time you call it, tells you what the stack trace is the next time that code hits a safe point. Okay? You can't get the information at any other point in time with that normal API. So that's a bias in terms of your sampling information. You will only ever be told it's running at a certain point in time when it's running. Now most people will tell you, don't worry, Richard. Safe points are pretty frequent in your application. It doesn't really matter. And sometimes they are frequent in your application. They should be at the head of every method. They should be on the callback edge of a loop. But in order to save time, the JVM optimizes out certain safe points. If you've got what's known as a counted loop, so for in I equals 0, I less than some number I plus, if that number is known at JIT compile time, that's a counted loop. It will optimize away the safe point at the head of that loop. Sometimes you can get applications that run for a while before they encounter safe points. Not all the time, but sometimes. Either way, it's a bias. And the other problem is, the way getAllStackTraces works, or at least the way it's worked in certain JVM implementations, is it doesn't do one save point for the entire JVM. Okay? It does one save point at the beginning to get the threads, and then one save point per thread. Okay? So you get this n+1 save point type problem of telling you, of pausing your application. And these save points can stall the application for a while. Okay? It's like times when, have you ever been in a meeting and nearly everyone who's meant to be in the meeting is there and they're ready to go, and you're just waiting for one person to get to the meeting? That's what the save point pause can sometimes feel like. There's one thread lagging along that you need to get into that meeting. It's a bias that will slow your application down. It has a big overhead. It can have a big impact if you profile regularly. And the other thing about get or stat trace is because it's looking at all the threads in your Java code, it's not telling you what's actually on CPU. If you've got a thread there that's sleeping, it will tell you about that as well. So that's good in some ways, because if you have problems in your application where, for example, you've got lots of threads contending on a lock and they're blocking, or if you've got lots of sleeping time somewhere, that can tell you that, but it's not so good. It's not being honest about where the CPU time is being used. But don't worry, I've talked about basically two failed approaches. There are better approaches. There's 2 or 3 better approaches. So the first one we're going to talk about is what I would say is advanced statistical profiling. So, when you're profiling, you've got 2 problems to solve, right? The first problem to solve is how do you interrupt the thread, and the second problem to solve is how do you read the stack trace out from inside the thread. Now the quickest way, or the lowest overhead way of interrupting a thread is using the operating system signal handler mechanism. So Unix operating systems all have a signal called sigprof. So, if you want to shut down an application, you might send a kill or a kill-9, yeah? Send a signal to kill it. If you really want to get rid of it, you might kill it, you might want to send a 15. If you really want to kill it, you might want to send a kill with number 9 to really terminate the process. Sigprof is just a different kind of signal. But instead of being a signal that kills the process, it's a signal that will be sent periodically to the process. And that process itself can register a signal handler. It can say, look, when I receive this regular sigprof, run this body of code, this other handler for the signal handler. And that's when you walk the stack, okay? The JVM itself has a method built into it called async get call trace, that on a thread will walk its own stack in a very efficient and very fast manner. So you use sigprof to interrupt, and you use async get call trace to run the code. That will tell you what's actually running on the CPU. You can use other mechanisms in order to figure out what's running in terms of elapsed time or wall clock time. Much, much lower overhead, much more accurate, double thumbs up. Now, you can use open source tooling to get certain of these low overhead profiling tools. So traditional profilers tend to be pretty high overhead. JVisual VM, hprof, Twitter CPU profile, anything that uses the standard APIs will be pretty high overhead. But there's a bunch of open source tools that are much, much lower overhead. Async Profiler on GitHub, Honest Profiler on GitHub, which is a project that I partly run and wrote some of the code for. There's also Java Mission Control as well, which has now been open sourced, which is fantastic. There's also profiling support in the Linux kernel, okay? So perf is a tool that ships with Linux that uses, again, a sigprof-based mechanism to interrupt the stack and reads what's going on, records it, and keeps track of it. The problem is with perf that by default it uses debug information from native code, C++ code, in order to say this pointer in your stack corresponds to this actual method name somewhere in your code. So in order to use that in the JVM, where you don't have that C++ native code in your Java code, because it's been JIT compiled, you need an agent to look those things up. And there's a perf map agent, again on GitHub, that you can use to run perf with JVM code. Much, much lower overhead, really good. You can also use hardware events, cache misses, things like that. if you're really hardcore, really interested. But people aren't just put off by profiling production by the performance overhead. They're put off by a bunch of practical problems as well, right? Often, it's very, very hard to take some of those existing open source tools and have them fully connected up to your system in production. Generally, they require access to production, which not all developers have. And especially problematic is not running these tools permanently, because that means that you need to connect into production at a point in time when your system's going wrong, which is like the last time you want to be connecting into production, right? They can involve a lot of manual work, fiddly setup, hard to automate. A much better approach would be pre-connecting tools to a production system and profiling all the time. If we keep our profilers always on, we can see what's going on in production all the time. And that gives us great observability, great visibility, and enables a few other things as well. Firstly, it enables historical data. Sometimes if you look at a profile of what your application's doing, you look at the method and you're like, that method's being called a lot. Is that normal? And if you don't know what normal looks like, you can't say whether that's normal, right? You can't say whether that's good or bad, it's just common. It may not be a problem, but it's good to have historical data, context. You can look what happens with this data at a previous point in time. Especially important if you get periods in your application where you have bursty traffic. So for example, people who work in, say, financial trading systems often have a huge increase in traffic and workload when the non-farm payroll numbers come out in the US. For e-commerce, it's often, say, your Christmas or your Easter shopping time periods. I know some people who work in gambling companies where they have big peak load problems when things like the Cheltenham races happen in the UK, or whatever the important gambling event is on their system. Historical data enables you to correlate this data with other metrics, see what was going on at other points in time. And it means you can also do regression analysis. If you've released a new version of your software into production, you can see what that code is doing compared to the previous version of your software. You can perform that kind of profile level regression analysis that you wouldn't be able to do otherwise. Then there's aggregation, right? If you profile a process through a traditional desktop profiler, you profile one process. That's okay if you've just got one big box in production. But if you've got 10 microservices that are all scaled out to 5 different servers, you've got 50 different processes to profile, right? You want systems that aggregate and index that information and keep it together so you can see the big picture, what the whole application is doing, not just what one process is doing. And you can also put samples in context if you run an always-on system. You can put versions of your application associated with them. Environmental parameters, what's the type of machine, where's it based, what's its location. Desktop profiles, again, they just don't have this kind of information because it doesn't fit their usage model, right? Their usage model is running on a local machine, connecting up to it. Production profiling systems like APM tools, which have some of this kind of information, can do it. APM tools are often aware or connecting for when you release a new version, and they can keep track of that information. So, summary of this section is, productions profiling is possible. We've got the technical capabilities. We can use things like async call, get call trace. We can use things like perf. We can run it with low enough overhead to only slow your production system down by 1%, say, or maybe even less in some cases. Production profiling gives us a really deep insight into what's going on. A lot of technical problems exist because of the old desktop profiler-based model. We can overcome them with better tooling. Okay, so let's wrap up. What have I talked about? I talked about performance really mattering to your business. Why would you want to fix performance problems? Then we looked at the fact that development in production environments were totally different, right? Different hardware, hard to reproduce workloads, often different software, often different JVM behaviors, very different. Metrics were a way of monitoring production performance problems, but hard to action them. Instrumentation, like traditional APM tools offer, is really great. It gives you visibility, observability, but on the other hand, it can often have a very high overhead. Production profiling can solve that problem. It can give you actionable insights, like where in your code do you look at to solve the problem. I think we need a bit of an attitude shift on profiling and monitoring. Thinking about doing profiling in production and all the time. Okay? Performance solving shouldn't be ad hoc. It shouldn't be, oh dear, something's gone wrong, we'll just go connect up to production and we'll try and fix the problem there. It should be systematic. It should be a thought-through process where you can look at your metrics, narrow down your problem, look at your profiling data, see where in your code the real problem lies and fix that. It should be a proactive, not a reactive solution. By proactive, I don't mean prematurely optimize all your code so it's really fast. I mean making sure you have the tooling in place and the systems in place so that when bad things happen in production, you know what's happened, you can fix those problems. When I say reactive, I don't mean RxJava, Spring 5, fancy frameworks. I mean reactive as in, everything's going along fine, it's all fine and dandy, oh no, we've got a problem, what do we do now? Reactive in that sense. And the best way of solving those kind of problems is by having always-on systems. And production profiling can be part of those always-on systems and give you valuable insights. What I'm basically saying is, please do production profiling. It'll be really, really useful to your organization. It can really help you and really save you time. And if you're running all the time in production, that's got even bigger benefits. Now, I mentioned a few open source tools, but I also run a business called Opsium. We do production profiling systems, so if anyone's interested in trying out our tools or just talking to me about it, come and ask me about it after the talk. I'm happy to have any questions or talk to you about it. Thank you very much. And if anybody has any questions, you can ask them now. What's your question in the back, sir?
Hey, thanks, very interesting talk. So you mentioned that we can do statistical profiling by capturing stack traces all the time.
Yeah.
And you also mentioned that there is a workload time and a CPU time. But how should we get a CPU time if we take a stack traces? So you mentioned it's possible, or I misunderstood.
So CPU time is pretty easy. So sigprof, as in the Unix profiling signal, when you tell your OS to send you sigprof, it will send you sigprof to what threads are on the CPU based upon the actual time that they're on CPU. It won't send them to things that aren't being called. So by default, out of the box, it gives you CPU time. Does that make sense?
Okay. And you also mentioned there is a memory profiling. So could you briefly give an idea of how does it work?
How does memory profiling work? It depends how it's implemented, is the answer. So most memory profilers, I mean, things like JDBC or VM, most of the way their memory profiles usually work is they basically instrument all the code in your application and then just record when objects are being allocated, which obviously has a very high overhead. Some memory profilers do that statistically. So, for example, they only keep track of certain allocation points, or they say 1 in 1,000 objects will say record the stack trace to see where that's going from. There are other approaches to memory profiling. So the approach taken by Java Mission Control and also implemented in the async profiler as well is when objects in the JVM get allocated, they get allocated in a space called a TLAB, a thread local allocation buffer, not to be confused with the TLB, which is a CPU feature. So TLABs eventually get copied off to another memory space within your JVM heap, and what they do is they wait for that TLAB to be copied and then just sample what objects are in the TLAB. So that's another approach to memory profiling, and one that's significantly lower overhead than the traditional approaches, but which has its own downsides. For example, because you're sampling when the TLAB gets copied, you can't tell exactly what stack trace is causing that TLAB. I've previously done consulting work for people where we had specific memory profilers. So for example, suppose you're looking for your memory profiling to find a memory leak. You know the type of the object that's being leaked because you can just see its usage going up in your CPU graph. You just profile for that specific type of object and have a profile that digs for that, which is massively lower overhead than a general memory profiler. So there are different ways of skinning that cat, and doing much lower overhead. And those are the three kind of ways. Okay, I said the questions, but I think I've just run out of time on the first question. So if anyone else has any questions,